Is the talent happy with the temperature in here?
Yeah. Assume you meant me.
Yes, you're the talent in this. If this was a professional shoot, that's what you'd be referred to.
Are we? So we're on, aren't we?
Yeah. So you need to get him to record his audio and start the Zoom.
Okay, I'm going to admit him now. Excellent. So yeah, thanks for joining me, Martin. I guess it's been a very busy and exciting time for you at the moment with the James Webb telescope.
It's certainly been busy. Exciting is one word for it. Nerve-wracking would be another word.
What kind of nerves are involved in this? What is your sort of involvement in? Because I know that you've been tweeting stuff and you've been very on the ball with it all. But what has been your sort of direct?
So there are two things. Leicester University, where I work, we have been part of the team that built one of the instruments that will record the light that comes in through the telescope to do the science with. So it's very important for us that the telescope works so that we can use our instrument. But I also work very closely with an organisation called the Space Telescope Science Institute, which is based in Baltimore in the USA, and the Mission Operations Centre for James Webb is actually located in that institute. So I've spent a lot of time overviewing what the preparations have been for the Mission Operations Centre and all this critical stuff around the launch, opening the sunshade, unfolding the telescope has really been at the top of our minds for quite a long time.
Amazing. Okay, so yeah, nerve-wracking. How much money has been spent on this? I heard 10 billion, but you know how the news is. Sometimes
I think that's a pretty close estimate, although it's always hard to be particularly accurate because that's probably just the amount that NASA has spent on it. And I think it's important to remember it's not just NASA, it's an international project with big contributions from the European Space Agency, from the Canadian Space Agency, and also directly from the UK because of the work we've done on this particular instrument.
And is sort of Russia and China and the other countries, I mean, India has a space program as well, I believe. Have they pitched in, or is this is not the space race? Or
they haven't on this particular project, although we often do joint projects with these other agencies as well. But they chose not to be involved in this at the time when it was first starting out.
Okay. And this has been... the idea for this has been, I believe it's sort of decades in the making. Is that right?
Yeah, it depends how you define it. It's at least 25 years, but actually people were already thinking about what to do next before the Hubble Space Telescope was actually launched.
Right.
But it was only really after Hubble was launched that people started to get more serious about thinking what the future was, because these projects, as you can see, take such a long time to devise, to develop, and then to actually build.
And so these cameras and the tech that you're using on the telescope, obviously it's tech that's kind of when it was envisioned was 4K, and I mean I don't know what the spec of the cameras and everything is on there, but is this stuff that they just sort of were assuming would be in existence by the time it got off the ground? Is it like the last piece to go in?
Well, you try to devise things to make them as future-proof as possible, because you're right. If you put in the cameras that were available 25 years ago, you probably wouldn't have such a good telescope. The images will be much less detailed. So we do try to delay building in those last few items as long as possible in the program. But we do have to close things off 2 or 3 years before we actually launch, because all those instruments have to be collected together. They have to be integrated into a package. That package then has to be added to the optics of the telescope. And that all takes many months and over several years for it all to happen. And then for it all to be tested to make sure, as far as possible, that it's going to work perfectly, as it seems to have done, at least so far, in space. That's a few years' effort to actually get from that point of bringing everything together to getting the project ready to launch.
And are you able to? Is it sort of branded stuff in there, or is it stuff that you can't mention, or is it all sort of? Is it kind of custom built things? So it's not like Kodak, or it's not.
It's a bit of both. I mean, we don't tend to use branded stuff in the sense of companies that make cameras don't generally make this kind of camera for the purposes that we want to apply to it. So we build our own cameras to our own specification and design. But the guts of those, the chips, the CCDs or the CMOS detectors, they come from a standard manufacturer, usually from Teledyne E2V, which seems to supply most of these things across the world at the moment. But that's usefully based in the UK. So the UK has a big manufacturing capability in these sensors that we use in cameras like these.
Amazing! I love that. So it's a real soup of parts and bits and pieces, and
That's right.
And has there been any innovation on the tech side that you think will make its way into a more domestic domain, do you think, from this stuff? Because you've had to make some real inroads, I imagine.
Yeah, it is a bit hard to say because you're looking over a long time scale. But the kind of imaging systems that we were using 20 years ago are what you've got in your mobile phone today.
Right.
And all the high-tech digital camera stuff, the stuff that goes into your mobile phone, the miniaturization of the components that are in your mobile phone, the reliability and the ruggedness of those components comes largely out of the space programs because we have to build stuff that's going to go into extreme places. It's going to be bombarded with radiation. Space is a very inhospitable environment from that point of view. It's going to be exposed to extremes of heat and cold at various stages. And also we have to make things very light and compact because it costs a lot to put things into space. And so you want to make these things as small and compact, at least in terms of electronics, as possible. Obviously, we just launched a very, very big telescope, which is a bit counter to that idea, but that's because we need a big telescope to collect lots of light.
Right. Interesting. I love this. This is great. I saw an interview with you earlier. I think it was with you. I've been trying to cram in as much as I can because I'm not a physicist, or I'm not, I don't have the pedigree that you have in the field. So you were very careful, I think, to mention that this is a successor to the Hubble.
Yeah.
And not a replacement. Is this because technically that's true, or does that come from sort of respect and stuff for the Hubble? Because it is a very important.
It's a little bit of both, but it is quite technical. I mean, firstly, Hubble is still working, and although we can't guarantee it, we hope it will work for another 5 years, and maybe it will work for even 10 years. So it's actually quite important that these two telescopes are working together. Hubble is different because it covers a different part of the spectrum. So James Webb is specifically designed to look in the infrared. So it's looking at radiation that comes from a part of the spectrum that we can't see. Whereas Hubble mainly works in the visible part of the spectrum, does a little bit of infrared, but it also does ultraviolet as well. So it has different capabilities, and actually joining the capabilities together is quite a powerful thing to do if you have Hubble and James Webb working in tandem. So that's why I speak of it as a successor rather than a replacement. Right. So the science is different and the capabilities are quite different. And that's because James Webb has been designed to do some very interesting things. It's been designed to look at the very first stars and galaxies in the universe, which we need to observe in the infrared part of the spectrum. And that's one of its key goals.
And I've heard the term redshift, I think, thrown around quite a bit. And I did watch something, and there was a lot of graphs coming on the screen and a lot of heavy terminology. And I'm not going to lie, I think I got the basic idea of it, but there was a lot of a lot of chat about redshift, and
Yeah,
some of it did go over my head.
It's very difficult to explain this without flapping your hands a lot.
Right.
But basically, because the universe is expanding, then the further away an object is from us, the more the light that it is emitted is shifted into the red. And if you shift it far enough, it ends up in the infrared part of the spectrum. So the most distant objects in the universe are appearing to travel away from us the fastest. And so that light is shifted way into the red, beyond the visible part of the spectrum, and into this infrared region that James Webb covers.
I see. And these very old stars, and is it quasars that you're looking for?
Well, quasars are some of the objects that we're looking for, because they are essentially a little bit like lighthouses, because they're relatively bright objects and you can observe them over the greatest distances in the universe.
I see. And so I've heard that the light that's coming from them has taken the entire sort of age of the universe to travel to us. And so I'm assuming it would be, if you think of it as a signal to analyze, it would be the purest thing to analyze, to take us way back to the beginning. Is this correct?
It really is a bit like time travel, because it's taken so long for the radiation to get to us. We're talking about 9 or 10 billion years since that light set out, and it finally reaches us 10 billion years later. So we're looking at objects essentially doing what they were doing 10 billion years ago. And so that does allow us to actually observe things that were happening soon after the Big Bang, when the first stars were forming, which we know very little about. We haven't been able to observe this with what we currently have available to us. And then we want to know how those stars collect into galaxies. And ultimately, it's all about understanding why the universe looks like it does today, because we can look at nearby galaxies, large collections of stars. We can look around in our own galaxy, and we find planets orbiting other stars in our own galaxy. But how did it all get to be like this is still a question that we need to answer.
That's the question, isn't it? You're trying to answer.
It's a bit like the Douglas Adams question. Yeah, life, the universe, and everything.
That is stunning. So as you said, the universe is constant, is expanding, and so by that nature, I guess what you mean is that things are getting further apart. Things are drifting away from us.
Yeah, although I would say it's that space is expanding. Space is expanding. It gives us the impression that things are getting further away. So it's a bit more like if you had a balloon and you painted a few dots on a balloon to represent the stars and galaxies, and then you inflated the balloon, you would see the skin of the balloon would stretch and these stars would move further apart. That's a little bit what's happening with the three-dimensional space of the universe.
Okay. All right. So would it be, so if we're going off the idea that the Big Bang is the creation of the universe, and you say space is expanding still, would I be right in thinking that we might still be inside a Big Bang of some sorts?
Well, we do believe the Big Bang happened. We definitely haven't gone off that idea.
Right, good.
The Big Bang as an event that marks the beginning of time of the particular universe that we occupy. That's clear. There is that beginning to us that we can look back towards. We'll never be able to see it, because the closer you get to it, the more difficult it gets to actually do any observations.
Right.
And even with James Webb, yes, we can look back close, but there's still a limit with what we can do with the James Webb Space Telescope.
Okay. And I might be going a little bit over my head with this next question, but I heard dark matter being thrown about quite a bit as well. And is this telescope going to be able to sort of pick this up, or is it just finds evidence that it has had an impact somewhere?
It will be more about finding the evidence.
Right.
The challenge about dark matter is it's very hard to detect. So we actually don't know what it is at the moment.
Right.
We know it exists because we see how it influences movement around galaxies. So we see the effect of its gravity on things that we can detect, like stars moving around. So we know it's there, but it's implied. There are lots of theories about what it is, but no actual proof of that any of these things are actually correct.
Okay.
And that's still a challenge. So James Webb isn't designed to detect dark matter directly. It will see the influence of dark matter on the evolution of the universe through the things that it observes.
Okay. And what do you think dark matter is?
So one of the possibilities is related to particle physics. It may be what we call exotic particles, things that you can postulate might exist theoretically, but they don't interact very strongly with the kind of normal matter we're used to dealing with. So that's why it's very hard to detect them.
Right.
I actually don't have a particular preferred model. I'm very much an observer. What I like to do is look at the theories and see if there are any predictions that I can then go out and observe. I work on groups of stars called white dwarfs that are essentially basically hot objects that cool down. They're dead stars, so they cool down over a long period of time. And it may be that dark matter affects the cooling of the white dwarfs, if it exists, or if it exists in a certain form. So we've been trying to see if the rate of cooling is affected, but that's a very challenging observation to make, and we haven't actually succeeded in demonstrating anything. But that's the kind of thing that we look for. Predict something, and then we can try to measure the effects of that prediction, and that might or might not prove one of these theories. But I think we're only just at the beginning of trying to do that. I think we've got quite a long way to go before we actually
on the cusp. So forgive me if this may sound a little pedestrian, but how much of Einstein and Hawking's theories are at play in what you're doing? And is there a chance? Because there was a few years back where I read some stuff and it was like, oh, Einstein might have been wrong, and then a few years later it's like, no, we think now Einstein might be right again. And so, how many schools of thought do you think will be shifted throughout this?
I think in astrophysics, people are pretty comfortable with the fact that Einstein's theory of relativity, well, his two theories of relativity, special and general, work pretty well.
Right.
Hawking is much more about the very fundamental beginnings of Big Bang, which observationally we still can't really go there, as I was already saying. But there are areas where what we see does confront the complexities of theories, like Einstein's general theory of relativity. So we talked a little bit about the universe expanding, and for a long time that fitted very nicely with the general theory of relativity. And the big question was, okay, is there enough matter in the universe to cause the universe to collapse again eventually? Or will it just keep on going forever because there's not enough matter, i.e. not enough gravity, to slow down the expansion and stop it? And so with Hubble and ground-based telescopes, astronomers set out to measure the expansion rate of the universe very accurately. And what they'd found was that it's not slowing down, it's actually accelerating. And theoretically, it can't accelerate. Einstein tells you it cannot accelerate, yet it is. And so the concept of dark energy was created to not really explain this, because we don't know what it is, so it's not an explanation. But it's an idea that there must be something, an extra force or something that we don't really understand, that is actually acting in an opposite way to gravity and making the universe's expansion accelerate. So that's an area where Einstein doesn't quite work. So there's a bit missing, I would say, from Einstein's theory of general relativity that doesn't sort of predict dark energy, which we now know exists from the observations that we've made. So that there are always these challenges around the boundaries of our observations and the boundaries of what we know. Now, that doesn't mean Einstein was wrong.
Right.
You know, what Einstein's theories work perfectly well in certain situations. And it's a bit like the transition between Newton and Einstein. Newton's theory worked really, really well for most applications and understanding how the planets move around the solar system, until you start to look at Mercury, which is very close to the sun. And then people realized that Newton didn't quite work for Mercury, and spent a lot of time struggling to understand why. And that's where Einstein's general theory of relativity came in, because it added the effects of the sun's gravity, the fact that the gravity is so strong when you're close to the sun that it stretches space and just makes things behave a little differently to Newton's predictions. So we're in a similar situation. So Einstein works pretty well, but when you start to look at things on the scale of the entire universe, there's something else going on that Einstein didn't know about.
Oh, this is great. This is great. I love this. So you say dark matter and dark energy. Now, in my head, I'm thinking, oh, that sounds like it's bad. Like, the dark side, bad connotation. Is this stuff? This is good stuff? It's not destructive stuff. What is it by? What's the nature of this stuff? I guess if you don't know what it is.
Well, we don't know what it is. It's hard to say the nature, but I wouldn't call it destructive. I wouldn't necessarily say it was good either. It's
right.
It's a feature of the universe. On the scales that we live, and on the time scales that we live, it's going to have absolutely no effect on us. So when we talk about the effect of dark matter, we're talking about effects that work on the scale of the entire galaxy, that are just the way stars move around in the galaxy. So it doesn't really affect us, except over very long time scales of hundreds of millions and billions of years. And similarly, dark energy doesn't really affect us either, because we're talking about the effects that take place over the entire lifetime of the universe. And we don't see those things working on the sort of years and decades and maybe a century timescales that are relevant to humans.
Okay, maybe I'll steer it back to the telescope, because we may be entering some sort of physics black hole of our own. But tell me about some of the engineering challenges for this telescope. If the listener's never seen the telescope, how would you describe it to them? It's quite it's the size of a tennis court. Is that right? It's large.
Yes. So the telescope is what we call a reflecting telescope. That is, it works using a mirror rather than lenses. And all reflecting telescopes have two mirrors, at least. A very large one, which is what collects the light coming in from the universe. And then it focuses that light onto a second mirror that then directs the light into some instrument to record what it is we're seeing, whether it's an image or it could be a spectrum from an object like a star. And so the James Webb Space Telescope has a mirror that is 6.5 meters in diameter. So it's huge. It's the largest telescope mirror that's been built so far. To keep it cool, because it works in the infrared, if we let it warm up, all we see is infrared radiation from the mirror itself and from the structure. So we have to cool the whole thing down and get rid of its own internal infrared radiation so that we can actually see what's coming to us from the universe. So to protect it, it has an enormous sunshade, which is made up of 5 layers of sort of aluminized plastic. And these layers are the tennis court size protection for the mirror. And that was one of the technical problems. How do you get that into space? And then how do you open it up? You can't actually launch something that's the size of a tennis court. We don't have any rockets big enough. And in fact, you can't even launch the 6.5 meter mirror ready to go, because that's much larger than the capability of the largest rockets we have. So we've had to fold the whole thing up and make it as compact as we can to fit into the Ariane 5 rocket that was used to launch it. And one way I've described it, which I think works quite nicely, think about a butterfly in a chrysalis. It's a very compact tube is a chrysalis with a solid shell, and inside that is a complete butterfly. And when the chrysalis pops open, basically the butterfly has to stretch out and unfold its wings before it can become a real living creature and able to carry on its life the way we'd expect. And that's really what we're doing with James Webb Space Telescope. We've folded it up as tightly as we possibly can, and we've put it in a tube that is effectively the chrysalis, and then we've thrown that into space on top of a gigantic firework. And then we've opened up the chrysalis in space, and gradually, slowly, because it's a very complex and tricky process, we've gradually unfolded that chrysalis into the butterfly.
You're talking about the rocket that the firework, as you said, to send it up. When you're looking at these things, do you have like a range of options of way? Is there different rockets that you can use? Different there are. This is the best one for this job, or this.
Yeah, there are rockets with a range of capabilities that are essentially you choose the right rocket for the size of payload that you want to fly. And if it's 100 kilograms, you use a smaller rocket than if it's a ton or even 10 tons. You have to have a bigger rocket. And also that relates not just to the mass, but also to the physical size as well. But of course, James Webb is the largest telescope we've ever put into space. So we're operating right at the top end of what rockets are capable of at the moment. And so the Ariane 5 is one of the most powerful rockets available around the world, if not the most powerful. There are a couple which are close to it. But it's also got the largest spatial capacity that was available. So it was the only one really that we could use to launch James Webb because of this need to fold it up. Other rockets would have had to try to fold it even more tightly, which we couldn't do. So there was a bit of a sort of a practical and technical feasibility issue around, can we find a rocket big enough to launch this telescope?
And so, as you said, it's the biggest telescope, and you're right at like you said, at the cusp of capability of modern rockets. What does this mean going forward now? Does this mean that we have to think about innovating their, what would you call it, like a delivery system? Is there like
Well, there's always work going on looking at what to do next in terms of rockets. And in fact, Ariane 5 is coming to the end of its working lifetime and will be replaced in a year or two by something called Ariane 6, which actually might not be quite as big because payload sizes are being reduced as people get more and more clever at making things smaller. But on the other side of that coin, there is a need for human exploration deeper out into space, being led by NASA right now. So NASA are looking at the development of larger rockets for the human exploration program that will take the large capsules that can carry 6 or 7 people out to the moon, or even further than that. So those development programs are going on at the moment. And in fact, some of the technology already exists, but it wasn't sufficiently proven to launch James Webb at this time. If you're going to put a £10 billion telescope on top of a rocket, you want to be sure that rocket has been very reliable, it's flown a lot of times, you can predict that it's going to work to a very high degree, whereas it's a much bigger risk to put it on some of the emerging technology. And you wouldn't want to use that right now. But in 10 years' time, when NASA has flown the Orion missions several times, and those rockets have been tested and used more and more, then there will be things that you can use to launch the next generation of space telescopes. And we were already looking at a bigger telescope than James Webb for launch in the sort of 2040s. Because if you don't start planning now, you won't be able to do it in 2040.
Amazing. Tell me a little bit about space junk. Is there any bits on this that's gone up that now it's going to be staying up there, or have you managed to minimise this? Right.
Yeah, it will.
Because I know obviously it's going to the telescope is going to stay in space for a long time.
Because it's going a long way from the Earth. It's going to be 1 million miles from the Earth when it gets to this what we call the L2 point, which actually follows the. It's actually not in orbit around the Earth. It's in orbit around. It will be in orbit around the Sun. And it will track the Earth. So if you imagine the Earth going around the Sun once a year, then the James Webb Space Telescope will be 1 million miles further away from the Sun than the Earth is. And it will follow the Earth around in its orbit.
Okay. And is that the Lagrange point? Is that right?
Lagrange point.
And how, because these are things that cannot be seen, these gravitational, I don't know what you call it, like a highway or something, or a tether, or how do you know that they're there? What's the obviously the maths is going to be far too sophisticated for me to understand here, but
well, it's not that sophisticated. It's actually Newton's laws that work there. It's not even relativity. So it's really just about gravity and the gravitational pull from the Sun and the Earth that creates a stable point. It's not completely stable, because if we didn't do anything, then the telescope will drift away. So it has fuel on board that we use to keep it in the position that we want it. And so the telescope will have a finite lifetime, because eventually we'll run out of fuel. And then we won't be able to control it any longer. And it will just drift off into space, at which point we'll shut it down, I guess. However, the launch was so perfect, and so little of the observatory's own fuel has had to be used to get it to L2, that we're actually predicting a 20-year lifetime for the station-keeping gas,
which would put you on track for about 2040 when you've put this successor on.
Nice.
Lovely, seamless. There's some rare materials on this satellite, and I think maybe it was you, perhaps it was someone else, who mentioned future space raiders may find it and dismantle it for.
Well, certainly quite a lot of beryllium in it.
Right. Okay. Tell me about this.
Because the mirrors needed to be very, very lightweight. For ground-based telescopes, and actually even for Hubble, we made mirrors out of glass.
Right.
Special glasses like something called zero-dur is one that we use. And sometimes we cast them in a kind of light honeycomb type structure, but they're still a solid single mirror and they weigh a lot. We couldn't do that for James Webb. It would have been just too heavy. So these mirrors are made out of a light metal called beryllium. Beryllium is quite a scarce material, very valuable. So yes, I can imagine maybe in the future people might want to go and cannibalize the telescope for its spare beryllium at some point.
Yes, sort of brings me back to the space junk thing.
Yeah.
There may be the equivalent of a Netflix show where they find old satellites and restore them.
Well, there's more to the reality of that than you might think. Right?
Really?
It doesn't really concern James Webb because it's so far away from the Earth that it's way out of the zone where space junk is important to us.
Right.
And space junk is really in the sort of low Earth orbit area, a few hundred kilometres to about 1,000 kilometres above the surface of the Earth. And that's where most satellites have been until very recently. And so there are lots of dead satellites. That's where rocket stages end up. Sometimes in the past they've exploded and created smaller fields of debris, and they're travelling very fast. So there is lots of risk around collisions with space debris in low Earth orbit, and a lot of concern about whether the amount of space debris will increase. And every time somebody either a satellite blows up accidentally, or sometimes an agency deliberately, like the Chinese or the Russians did recently, destroy one of their own satellites to show that they can do it. You create more debris, and the more satellites you have, the more likely it is that you'll have collisions. And then there is a lot of work going on to work out, well, firstly, how to make sure that new satellites don't become debris in the future.
Yeah.
So rules that we have to abide by to make sure that a satellite will eventually drop out of orbit safely. And also concern about recovering debris that's already out there, but is what you might call historical debris that couldn't follow these rules because they didn't exist. And how do we recover that? And how do we keep space safe?
Yeah, I imagine, is there some sort of data which it sort of tells you the position of all of the known space junk? Because if you're firing something, if you're launching this rocket, the last thing and I'm assuming if it's caught in an orbit, it, like you said, it's going very, very fast. So, forgive me if it's a little naive, but say someone was trying to repair something on the space station and a nut or bolt floated off or whatever and it's got into that would be like a speeding bullet, wouldn't it?
Yes.
Orbiting.
Yeah.
And that would just tear through anything that it comes into contact with.
Yeah, that's exactly the problem.
Right.
And just to sort of comment on what you just said, when the Russians destroyed the satellite, it created sufficient debris nearby the space station or in an orbit that cut across the space station's orbit that they actually took precautions to confine the astronauts to a very limited part of the space station and then closed off some of the parts that they didn't actually need to use because they felt they might have to abandon the space station quickly if there was some collision. So there was actually serious concern about risk to the astronauts. And the irony there is, of course, there were Russians on board the International Space Station. So the Russians had created a cloud of debris that was actually putting their own citizens at risk, never mind anybody else's. So that was all a bit strange and bizarre. But yes, you're right. And this is the problem. The speeds are high and the damage can be quite severe. So debris is tracked, but there's a limit to the size of piece of debris that you can track. You cannot track a bolt or a nut. It's too small. The logistical situation of how many pieces of small debris there are. Yeah, there are 2,000 or 3,000 satellites in orbit. There are probably tens of thousands of trackable pieces of debris. Who knows how much isn't trackable because it's even smaller than that. But if a satellite blows up, you do get a lot of small particles of debris, pieces of the covers, bits of foil. Most spacecraft are covered by thermal blankets, which are basically metallic foils, and they fragment into small pieces. And those things form most of the debris that we're concerned about.
I know we're digressing a little bit. My curiosity is getting the better of me here. But in terms of space junk, what's the answer then? If these things are flying around and there's loads of it, because I've seen some pictures of like the data, proposed data, and there's a lot of stuff out there.
We don't have a full answer to it. I mean, there are a number of parts to the answer. The first part of the answer is don't produce it. So the rules and regulations around what you put into space and how long it can stay there are important. But of course, everybody has to abide by them. And certain regimes, if I can be polite about it, why should I be polite about it? Certain idiot regimes that think it's fun or politically useful to show that they can destroy a satellite in orbit are really playing with fire. And they shouldn't do it. But unfortunately, we don't have control over the Russians or the Chinese. Most people in the sort of community I work with tend to play the game, but you can't rule out these rogue activities, and that's one of the challenges. So we do need to also look at the problem of how do we recover the debris. There are some good ideas that are being tested now for recovering whole satellites. So you can have a vehicle in orbit that can go and capture a satellite and give it a kick that makes it drop out of orbit. But we haven't done it yet. We're still in the early days of demonstrating that, and there are some demonstration programs that are going on at the moment, and we'll probably see some demonstrations of that in the next year or two. So we're getting quite close to testing some of those ideas in space. But that doesn't solve the problem for the large volume of small debris in space, as Douglas Adams, I've quoted Douglas Adams once already, but as his Hitchhiker's Guide says, space is big. It's very big.
Yeah.
And although we're concerned about what's happening in a relatively small part of it, low Earth orbit, it's still a large volume that's filled by that debris. And trying to hoover debris over such a large volume is conceptually a very difficult challenge. I can't actually myself imagine quite how we would do that, and how many space vacuums we would need to actually put up there to solve the problem. And I think that's going to be something that is around for decades, maybe hundreds of years, which is why people shouldn't go around blowing up satellites.
Right. No, it just seems like a bad idea, doesn't it? And I don't even know much about this stuff, but if you ask me that, hey Andy, should we blow up that? I'd be like, no, this is a stupid idea. Is this why the SpaceX stuff, the Elon Musk stuff, is quite exciting? Because those the sort of reusable, and we all seen, well, we haven't all, but a lot of us have seen the footage of the I can't remember what the rocket was called.
Falcon.
The Falcon, I thought so. Landing back down, kind of a bit like Thunderbird 1 or whatever it is. Is that something that's been produced to tackle this space junk issue? And I know you've done some work for Elon Musk or with some Elon Musk.
Well, we've been looking at this, and SpaceX have been cooperating with us. So yes, it's exciting. There's a lot of excitement around it. The constellations of satellites that Elon Musk is putting up are really designed to improve accessibility to communications, particularly if you live in a part of the world where you don't have good ground infrastructure. The ability to use satellites to get your internet and get your communications is going to be really, really profound for certain countries. Perhaps less so for us in the UK, where we have good sort of ground infrastructure in most places. But if you live in northern Scotland and you don't get good internet, then satellite internet might well be the way forward for you. So it's very exciting. At the same time, it's also concerning. And this is why we're working closely with Elon Musk to look at some of or his organisation, not directly with him, to look at some of these things, because these large constellations pose a threat from a space debris point of view. If something goes wrong and they can't deorbit, can they create more debris? And I think they're doing everything they can to prevent that. But there is this little thing at the back of your mind about accidents will happen eventually when you've got a large number of satellites. If you've got thousands of satellites and you've got a low but finite chance of things falling apart or breaking and not being deorbited, then it will happen eventually. So there's that challenge. It's also a challenge for astronomy that these satellites are quite bright. And so they actually can interfere with astronomical observations from the ground.
Oh, so they can create their own sort of light pollution.
Yeah, so it's a form of light pollution. Right. And it's already a challenge, but as these numbers grow, it's going to get even more difficult for ground-based astronomers. And as we build larger telescopes on the ground with larger fields of view, then it could become impossible to do some of the science that we currently want to do. So I would say it's a bit of a double-edged sword. Lots of benefit for humanity in some senses, but also lots of risk in others. And getting the balance right is still something that we have to do, I think.
Totally. I mean, just imagine that you live in an impoverished third world country, and all of a sudden you have access to the internet in your hand.
Yeah, absolutely.
Imagine the educational benefits to a huge percentage of mankind.
Yeah, and That's why
Game changer.
I'm not an advocate for stopping people like Elon Musk and others, he's not alone,
Yeah.
doing this, because how can I argue against benefiting somebody in sub-Saharan Africa whose life is already pretty shit, if I can use that word, from improving their existence and being able to modernise and being able to live a better life? How can I argue against that? I wouldn't dream of it.
Yeah. And it's opportunity as well, isn't it? Because, it's the old saying, knowledge is power. And it's, it's the ability to see industries and different, seize different economic opportunities that may be inspired from being able to educate yourself and see how the rest of the world are doing things.
But if we do produce too much space debris, then we won't be able to operate satellites in those orbits any longer. And so everybody would lose that. So it's not just about looking after the astronomers. So I think it's a balance. We have to try to work out how to balance this correctly so that we don't kill astronomy, we don't destroy low Earth orbit as a useful place, and we still benefit humanity through doing this stuff.
It's amazing, isn't it? We haven't even sorted out climate change and saved the issues that are happening here, and we're already discussing a risk of sort of destroying the next part of our playground, let's say.
But of course, space plays a big role in climate change monitoring and helping solve the climate crisis. So they are actually quite closely linked together.
So it's a balance, isn't it? I was going to ask you about sort of billionaires in space. What are your thoughts? I remember when I was a boy, I saw an advert with Stephen Hawking in it, and it was a sort of a CGI thing of him in a spaceship. It might have been a Virgin advert, and he was sort of in, I guess you'd call it a lower orbit or something. He's just, he was in space looking out the window as a space tourist, and that was kind of the first time for me that space tourism had been, the idea had come to me. And it seems that, the last couple of years we've sort of seen that a little bit. Famously William Shatner went to some part of space. Some people say he didn't really go to space. And then, we've had Branson and Richard Branson and Jeff Bezos. What do you think about these day trips to space? Do you look at it and think, you don't know what you're playing with here, or does it kind of excite you?
Again, I have mixed feelings about it. I think people like Elon Musk, in particular, who's focused rather more on the economics and creating systems that we just discussed for benefiting other people, as well as himself, because he expects to make money out of it. But I can get along much more. He has avoided the space tourism thing. I find the space tourism route slightly challenging because in the end, it's only going to be affordable for a relatively small number of people. And given the challenges we have on our planet, I find it a bit of a distraction. I think we need to do more in space. We need to make space more accessible, but we also need to make it more democratic in the sense of it needs to be accessible not to billionaires, but to everybody, people like you and me. I'm in a privileged position because governments give us money to launch things like the James Webb Space Telescope, but it needs to be relevant and useful to anybody who walks down the street. It's already an integral part of our economy, but it also needs to be that the case that any company that needs access to space to do its business or to deliver something needs to be able to do it. So we need to make getting into space cheaper. Satellites need to be smaller, cheaper. We need to be able to launch them more quickly. And we need to allow access to these things to small businesses, not the big businesses that we're used to seeing working in the space area. And that's I think, what needs to come out of, and it will come out of the work that Elon Musk is doing. And I think it will come out of the work that both Bezos and Richard Branson are doing, because behind the space tourism bit, there is quite a lot of really useful development going on around satellite launches and things like that don't hit the headlines in the way that they ought to, but actually I think are much more important than a few people going up on a space trip. Much, I have to say that if I was offered the chance, I would do it myself, because I'd love to go up into space. But I think we've got to focus on the wider benefits, personally.
Right. Yeah, I agree. If I mention colonizing Mars to you, will you roll your eyes and be like, "Oh, not this again"? Or is it something that you find plausible? Because I can't tell which
I would
side the
never roll
experts.
my eyes and say not this again, because every idea like that is something that might eventually set humanity on a useful path.
Right.
Maybe that people roll their eyes at Arthur C. Clarke when he talked about putting satellites in geostationary orbit when nobody ever built a satellite.
Right.
Never mind thought about what useful orbits could they occupy. I think colonizing Mars is a much longer term thing. I think the challenges of doing it are far more complex than people might admit. Because if you admit it, then you put it so far away that you don't even think about it.
Right.
So, but I think the idea of traveling to Mars is certainly feasible, but it's still a difficult thing to do. It's not a technology problem, really. It's a logistical problem. It's DHL and DPD and all those other things, because it's about getting enough gear out there to allow people to survive.
Right.
There are some technical issues around radiation that we would have to solve, but I don't think they're insuperable. But the big challenge is, how do you keep people alive and safe for the best part of 2 years when nobody can get to them if anything goes wrong?
Yes. Quite a scary prospect, isn't it?
It is. And I'm sure there are plenty of people who would take that risk because of the excitement of doing it and the excitement of being pioneers. That's why people climbed Everest and went to the moon and even got in a very, very sort of fragile boat and sailed across the Atlantic to America. So there are people that will do it, but I don't think we should underestimate how difficult it's going to be. And planning and cost are going to be a real sort of factor in deciding how quickly we're going to do it.
I think let's get off the planet. We need to start, exploring more of the, making bases or homes or colonies elsewhere. I think it's born out of a fairly nihilistic view of the way things are here on Earth. Does that make you? How do you feel about that?
I certainly think that we shouldn't treat getting off the planet and going somewhere else as a solution.
Right.
We've got to look after what we've got, because there is nothing like it anywhere else. Mars might look quite nice from a distance, but it's an extremely hostile place. The atmosphere is 1/100th of the pressure that we have on the surface of the Earth. You can't walk around on Mars without a spacesuit. It's going to be very hard. People talk about very sort of high-level science fiction things of terraforming Mars. I cannot ever see that happening, really.
Right.
Creating the volume of atmosphere that you require to be able to walk around the surface is just such a massive challenge. So we need to make sure that Earth is a habitable place for the foreseeable future. Otherwise, we will die out. You can't just go and stick the population of Earth on Mars. There just isn't the infrastructure to do it, and there probably never will be, I think, on that scale. I'm not against exploring at all. I think that's an important part of what we are and who we are. But we've got to look after what we've got.
Yeah, I agree. Do you think that the only way that we would achieve something so monumental like that is to possibly take a leaf out of the Star Trek book and realize that we're all one, and if we all pool our resources together, then we can head out.
Absolutely, and we to an extent, I think if you look around the space community, we actually already do that. There is a certain amount of nationalism associated with some of the things that we do. And clearly, agencies like NASA have more money than anybody else. But by getting together in organisations like the European Space Agency, we actually play pretty much on the same level as Europe. And I'm not talking about the European Union here, I'm talking about ESA, which is not the European Union, but is a different collection of European countries. And we build things, we've contributing to James Webb Space Telescope. ESA builds its own exciting missions on a par with the kind of things that NASA does. So we sent the Rosetta mission to a comet and landed on the comet. Absolutely, nobody else has done that. So pooling expertise, getting together, the International Space Station does what it says on the tin. It's international. There are Russian cosmonauts on there, American astronauts, European Space Agency people, Japanese have been up there, Middle Eastern astronauts. I can't remember if they've actually been Chinese astronauts. Possibly not. But yes, I think there's a recognition across space science that you have to tear down these boundaries and work more internationally. I think space community is actually a good example of how to do it.
Right. Amazing. And the moon, what use is the moon? I mean, I know we went to the moon in 1969 and had a wander around. Someone put a flag up there, apparently. What uses could the moon be to us? Will we go back? What's going on with that sort of stuff?
Well, we are going back. There's a plan.
Right. Okay.
So if the plan is executed, then people will set foot on the moon again. Chinese certainly want to go there. And for them, it's a bit of a reverse moon race. People have been there, but they want to show that they can do it as well.
Right.
And that's highly political from their perspective. But setting the politics to one side, there is value in going back to the moon to understand the moon scientifically. I'm less sort of convinced by commercial arguments about going to the moon, about exploiting the moon for its resources. On the other hand, it is a good test bed because it's nearby and it's relatively easy to get to and it's relatively easy to land on for doing things like trying out technologies for going to Mars and for understanding how to live in a hostile environment. And eventually some of that may become commercially useful. And there are certainly bodies in the solar system like asteroids where there are significant quantities of scarce elements that we might in future decades find it useful to go and mine those bodies to recover important things that only exist in very small traces on Earth. But it's hard to predict exactly when the cost becomes worth it compared to the benefits. But I've seen some calculations done about how you might mine asteroids, and they look quite plausible to me in the longer term, taken over timescales of the next 40 or 50 years.
It's the potential, and it's almost like space has this for the imagination. It's like space has an infinite amount of fun to be had.
Absolutely.
Yeah. I'm gonna ask you about aliens now. I know that you probably have been asked this a lot. Whenever something new in space happens, people go, "Oh, will we finally find aliens and things like that?" How do you feel about that? Do you get bored of it? Or
no, not at all. I talk about aliens a lot. I actually go out and talk in schools and to various groups about aliens, among other things. I talk about other things to do with space. But I think the question of, are we alone in the universe is a fundamental question that scientifically we need to answer, as well as philosophically. I think it's one of the biggest scientific questions going. Are we alone? Now, if you ask me what I think about aliens, then I can give you a couple of answers. I do think it is likely that there is life outside elsewhere in the universe. I think the chances are really pretty high, but hard to quantify with any accuracy. What I don't believe is that aliens have ever visited the Earth. I think there is absolutely no evidence And there's much evidence to the contrary that aliens have not visited the Earth. And I think that's partly because, as I said earlier, space is a massive place. It's very big. You can actually do some basic calculations with some reasonable assumptions about how long civilizations last, how many habitable planets there ought to be in the galaxy, about how many alien civilizations there might be at any one time. And the number always comes out to be very small. And that means that any civilizations that do exist are going to be pretty a long way apart, which makes communication and travel between them pretty much impossible. So I think aliens are likely to exist in some form or other, but the chances of communicating with them at all are very slim, because the time windows are too short. Civilizations tend to destroy themselves if you look historically. So I'm not that optimistic that humanity will be around for more than a few thousand years. So
Okay, but surely that idea would surely that negates all your work. What's the point in understanding anything if there's not going to be anyone around long term?
I would hope that we can not allow that to happen.
Right.
But I think we'd all have to accept that there's a significant probability based on the way humans behave, and we see it all around us every day. We see all the problems and challenges of the world that are actually created by people more than anything else. That subsection of humanity that just don't behave very well, or nicely, if you want to put it like that. It's got to be a possibility. So, but that doesn't mean to say we shouldn't try to stop it from happening, and we shouldn't try to create a future that is better for everybody, and improve our knowledge to actually allow people to move forward. Maybe we'll confound that prediction. So I think, yes, we should carry on generating the knowledge and thinking about what we do in the future. But as I said quite early on in our discussion, our horizons are quite short compared to the timescales of the universe. There is stuff going on out there that we may not realise and may affect us in ways that we can't possibly conceive of at this stage.
Some people say, maybe we shouldn't know everything. Maybe we shouldn't figure all of this stuff out. Which is obviously completely against your school of thought. How do you feel about that? If, say you figured it all out, do you think you'd be a bit disappointed?
Well, I think the main thing I could say is that we're never going to figure it all out. We'll figure bits of it out. We'll improve our knowledge, and we will make some really exciting discoveries about the universe. But we're never going to figure it all out. I think the universe is just so infinitely large that we'll push the boundaries, but we'll never get to the end of pushing the boundaries.
Good stuff. I like that, though. I do like that. I don't, we've got to have a mission, haven't we? We've got to stay curious.
Yeah. And obviously space is one part of a whole lot of science and understanding that we need to do. You think about hopefully it's all about improving people's lives in the end.
Yeah.
And although astronomy might look a bit obscure, it still makes its contribution to improving people's lives. It improves it from the point of view of what we think about ourselves. People are excited by astronomy. Isn't that improving people's lives because they've got something to be enthusiastic about, and they can see the wonder of the universe? And at the same time, it makes commercial. It does things that support them commercially and economically.
Amazing. The work you're doing here, it reminds me of that old saying, planting a tree which shade you will not.
Planting a tree whose shade you will never see. And as I said a little bit earlier on, we're planning the next space telescope. And that is the same kind of thing. I will never use it. Yeah. It's too far in the future. I will have retired. I hope I'm still around when it finally flies and I can see the results. Yeah. But it's something that my generation is thinking about now for generations of astronomers 20 years in the future. and for people 20 years in the future. So, yeah, I agree with you completely.
Yeah, and hopefully the stuff that the James Webb Telescope discovers will have a ripple effect and will be serving science and theories and discovery for many, many years beyond the next telescope.
I would hope so.
An enduring legacy, we hope. Thank you very much, Martin.
Well, it's been a great pleasure.
Thank you very much for your time. It has been a real honour to speak to you. Yeah, as I said, I'm not a physicist or an astronomer, and I've done my best with the knowledge I have to try and ask questions that you may not have been asked before, and also try and get some of the ones that we all want to know in there as well. But yeah, it's probably a good time to wrap this because I think that alarm is going to fuck this up. It's going to be an issue.
You won't be putting that on the podcast then.
Maybe. Well, we'll see.